Okay, so one of the things that pre-calc is concerned with is these waves. Like this one's a sine wave, and if I just shift it over a little bit, that would be cosine. And you're going to learn a lot more about that this year. Why would you ever see a wave like this in nature? Well, not just talking about waves like in a lake, but how about the tides? You know how they cycle? They start over and with the exact same pattern, like it's high tide, and then it slowly goes down. All of a sudden, it's low tide, and it slowly comes up, and it's high tide. And there's a regular period of time between each high tide. Okay, so that's something that goes with this picture. There's other things that we see in nature, like even just the sun setting and rising. You know, those are like kind of like waves. How bright it is outside, and then it gets. Now that's a little different because it holds that brightness for a long time, and then it gets dark, and then. All right. Sound waves are actually compression waves, but they are different. I'm going to encourage you to think about two things that I'm sure have happened to you at some point. You've probably been in the backyard and heard a little bird chirping. You know, there's just a high little that kind of noise. That kind of noise doesn't travel very far. On the other hand, you've probably heard a noise like a subwoofer coming from a long ways away. Some dude in their Honda Accord that's got the jack down low, and you hear the doop 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 kind of noise, and that's the subwoofer. You can hear those a long ways away. Why? Not because it's so loud. It's because lower noises travel way farther than high noises. It's one of the reasons why if I yell across the room and my wife yells across the room, like it's a huge difference. She's got a really high voice, and a low voice will travel way farther. That's why if two kids are talking in the back of the room, one's a girl, one's a guy, the guy usually gets yelled at and the girl doesn't, because the teacher can hear the guy and the girl can't hear. It's true. Not saying we can never hear the girls, but it's just low noises travel farther. Do you know that elephants talk in low noises and can talk to another elephant over 10 miles away? That'd be like you standing on the soccer field here in Minnetonka and communicating with a friend who's standing on the soccer field at Edina High School. No, that would work too, but at Eden Prairie High School. You could seriously yell to each other and hear each other. Elephants can do that. They can talk in super deep noises that you can't even hear with a human ear. They talk in, they can also make noises that are in our range, but they can talk in super low tones that travel super far. And it travels actually through the ground, and they think that the elephants use their legs are kind of almost like antennas and can pick up the vibrations that are coming through the ground, and it comes up through their legs and they can hear it in their ears. Anyway, there's lots of waves that are in nature, and the sine and the sinusoidal stuff that we're going to learn this year helps you to write equations for it. A couple of keys to success in here. One is do your homework. Some people get the idea that, oh, homework's only 15%, tests are 85%, so homework isn't worth much, and therefore it really doesn't matter. Totally false. Not only, of course, is it important to do your homework because it'll help you for your tests, but it also does make a difference on your grade. That 15%, if you didn't ever do any homework, what's the best you could get for a grade then? 85%, which would be what grade? A B. If you never did any homework and you were perfect on the test. Now, is that likely? If you never did any homework, would you be perfect on the test? No. But even if you could, it'd be a max of a B. And here's other proofs I can give you about why homework will make a difference. When I look at homework grades in last semester for pre-calc, a typical class would have about 5 kids that were only 0.5% away from the next grade up. And another 5 or so kids would be only 0.5% from the grade below. In other words, they barely made it to the grade that they had. So you see, if 0.5% can make a difference on your grade, then 15% can be huge. It can make a huge difference on your grade. So don't fall into the trap that homework doesn't matter. It totally does. Mathematically, it does. And it does count. Like what I assign you today will count and will go into the grade book. Okay, some people don't put it in the grade book, and then obviously it can't count. But it does go in the grade book. So make sure you do homework. And studying for tests, it's your decision. Obviously, I can't make you study for the test. I won't even know if you studied or not. But some kids, this is one of those life is not fair kind of moments where some kids can study for 5 minutes for a test and get an A, and other kids will have to study for 3 hours to get the A. So that all depends on you and how good you are at math. Because life isn't fair that way. Some people are born with amazing artistic talent. Other people will never be able to do that. They could try really, really, really hard and take lots of lessons and maybe someday get as good as the person was back before they took any lessons. You know, it's just, life isn't fair. So, same way, some of you are going to need to study more than others. That's just the way it is. But it all depends on what you want for a grade, too. A lot of you could probably coast through and get B's and C's without even really ever studying and be fine. But is B's and C's good enough for you? Is that what you want? Some of you really want to get into good schools, and those good schools are going to need to see high GPAs. And this is not a weighted grade class, and so this is one of those times where, you know, if you get less than an A, you're hurting your GPA. And it might make a difference to you on what college you want to go to. Even the U of M right now, for getting into their engineering school, requires around a 3.8 GPA. Just for perspective, 4.0 is perfect. And through weighted, you can get a little higher than that, but they require a 3.8. Even at the U, which used to be like relatively easy to get into. So it's getting to be, you know, there's a lot of colleges that would not be able to take you if you have a B average. So I know that most of you are going to be shooting for the A's, and that's how you can decide whether or not this is worth it, is how much do you care. All right, I expect respect. I will respect you, and I expect you to respect me, and also respect the people that are near you. So we're not going to go through a big list of what you can do and what you can't do, but I just expect that usually kids in at this level are not don't have a hard time figuring out what they should be doing, what they shouldn't be doing. Before I get into that, I want to actually look back at something here. So even if you go home today and you try to forget about math, even though you've got a little homework to do, and you go and find a, hold on just a second here, I'm looking for a particular song. Find a song on Pandora or whatever, and you just want to get away from math, you won't be able to do it by listening to music. Because music has tons of math in it. It's not just things like change that we can see in the tides going up and down, or the fact that you're getting taller right this second. Do you know that? You might be thinking, well, I'm not growing anymore. I've stopped growing. It's because when you're sleeping at night, I'm sorry, you're not getting taller, you're getting shorter. I said it backwards. When you're sleeping at night, you stretch out. The vertebrae in your back get a chance to like decompress. And when you wake up in the morning and you stand up, you're at your tallest. You just get shorter and shorter and shorter. So right this second, as you sit up, you're shrinking. How fast? Really, really slow. You're also giving off heat. Like right this minute, you are giving off the same amount of heat as a 100-watt light bulb. So if you all weren't in here, it would be much cooler than it is right now, because there's like this big bank of light bulbs burning here. So by the end of the day, it gets really hot. So I'm listening to my music, and if you can hear the beat is exactly the same distance apart every time. If you can't hear it at that speed, maybe you can see what I'm talking about here. And if you needed more evidence, what's this? A whole note. Implying there are notes that are not whole and are like fractions, right? How about this guy? I think this is a quarter note. If it was empty inside, it'd be a half note. I think. How about this one? this an eighth? How about this one? 16th. Look at that. Fractions in your music. There is so much math around you all the time. I just love this subject. One of the things that's also true is that it's hard to concentrate for long periods of time. They say, the research says, that you're able to concentrate for about your age plus or minus 5 minutes. For some of you, you're the plus 5 minutes, and some of you have a harder time paying attention near the minus 5 minutes. So that means your age, which is probably around 15, 16 or so, we can say that you can concentrate for probably 15 to 20 minutes. And if I go longer than that, you're just going to drift and drift and drift. So I'm going to take a short break. During that break time, I encourage you to get up, talk to your friends for a few minutes, and when we start up again, you'll be completely refreshed and able to concentrate again. All right? So take a short break. Okay, done with the break time and back. So what do all the things up here have in common? They're all mythical, yes. Or what's a math word for that? One math word that's kind of close to mythical or sort of like theoretical. Imaginary, yes. They're all imaginary. One kid argued on this one, but I don't know. I suppose if you're a Nessie believer, it might hurt to hear that it's imaginary, but anyway, there's been a lot of fake Nessies. That much we know for sure. Loch Ness monsters. People have tried to pass off. Back in the days before Photoshop, where it was actually kind of hard to fake a picture. People were like, "Oh my gosh, I saw a picture. It must be real." Nowadays, we're so used to Photoshopped pictures that it's like, no, of course that could be fake. Anyway, math numbers that are imaginary. These guys over here are a very small little group. In fact, the only one we expect you to know is something I'm about to tell you, and I want you to write down. So would you please take out your notes that you're going to keep for this class. This will be in a spiral notebook or even loose leaf that you keep together, but it should not be on just a stray sheet of paper that you pull out of the bottom of your backpack randomly. We want to keep these organized so that you know what to use to study for your tests. All right, so hopefully you got a nice notebook that you're going to label for math. And here's the first thing I want you to write down, and that's I. The letter I. And I bet you half of you could probably tell me what I is. And half of you probably have forgotten, and that's all right. You'll know in a second. What is it? Who's got it? Raise your hand if you know. I is imaginary, but what is it? Oh, no, we know what it is. I is actually defined as something. Yes. The square root of -1 is correct. Would you please write that down? I is defined as the square root of -1. So if I were to say, like, the square root of -25, I could say it's like the square root of regular 25, which is 5, and then the square root of -1. Because, see, I can break it up like this. And the square root of 25 is 5, and the square root of -1 is I. So it'd be I5, but we usually switch that around and say 5I. So there's an example of an imaginary problem. We don't do them very often, but scientists created these numbers so that they could solve problems in the real world. Isn't that weird? The thought that you have to have imaginary numbers to solve real problems, which is weird, but we're not going to get deep into it here. Notice that the rest of the numbers are called real as opposed to imaginary. That's all the rest of the numbers. And you do not have to know all of these subparts, but you do need to know this. Rational versus irrational. And rational numbers can be written blank. This is the thing you're supposed to know from before, but I know you might have forgotten. So since nobody seems to be answering, would you please write down rational numbers? Can be written as, and then some smart cookie will know this. It's kind of been a theme I've been pounding on through this whole day today. Yes. Fractions. Very good. Rational can be written as a fraction. There are so many fractions in the real world. right now, my batteries in my remote, would you agree that they're probably not 100% anymore because I've been using them? It's probably down to like 98%. Isn't that a fraction? It is. Any percent is a fraction. So if I said that, for instance, you, if I measured you with my ruler here, are probably not an exact number of inches, are you? You're probably like 67 and some fraction of an inch. The odds are not good you're going to be exactly like 67 inches. Okay? I'm about 70 inches-ish, but I guarantee you I'm not exactly. The odds are tremendously against being exactly 70 inches. So the point is that there's fractions all over the place. And math is one of those places that we got to get good at handling even complicated fractions. But why, again, in this diagram am I talking about fractions? Because rational numbers can be written as fractions. And irrationals can't. So what's irrational? Things like pi. You cannot write pi as a fraction because whenever you divide two numbers, you get this decimal that is not pi. You can't make it work. And if you can, there are going to be people that are willing to pay you millions of dollars for that information. Seriously. Because there are problems that they have where they really could use the next, like to be able to get pi even farther. They've already got it out like a billion places. But it actually would be a huge thing if you could figure out what two numbers would give you pi. Now you might think 22 over 7 gives you pi. But 22 over 7 just gives you a close, an approximation of pi. It's not the real deal. All right. Another thing that's irrational would be like the square root of 2. But it's not just 2. It's the square root of anything that doesn't come out nice. Like square root of 25 comes out nice. It's 5. And then it's rational. But square roots that don't come out nice, like square root of 7 or square root of 13, anything that's a square root that doesn't come out nice is irrational. All right, the rationals then are everything else. So how could you write a whole number like 3 as a fraction? Yes? Okay, where did pi come from? Pi is just simply a ratio that they noticed on a circle that whenever they took the distance around the circle and they divided it by the distance across the circle, it always came out to that number, 3.14. And so you take anything in the real world and you measure it around, you measure it across, you divide it, you get this magic number. It always comes up. 3.14159265358979323. I don't know any farther than that, but anyway, pi is really real world number because you can take anything that's a true circle, measure around it, measure across it, divide them, there it is. All right. There's a whole lot of numbers that are really cool like that. They come up all the time on the human being. And you got to remind me of that at some point. I can show you these amazing numbers that keep repeating whenever you divide certain like widths and lengths on your human body. There's a number like pi, except it's the human number. It's not pi. It's this ratio that comes up a bazillion times. Okay, anyway. So rational number versus irrational. Again, fractions matter. So moving on. In fractions, we got to know about reducing. I know you know how to do it, but I want you to think of reducing as canceling. So when I have 8/10, for instance, that could be written as 4/5. I know that. That's the answer. It's reduced. But how did I get there? I can get there by canceling. And the way I like to show that is to say 8 could be written as 4 times 2. 5 could be written as, 10 could be written as 5 times 2. And then, see that 2 and the 2 on top of each other? If I just take them apart and divide them, what do I get? 2 divided by 2 is 1. That's why those 2's can cancel. And they don't just disappear. Technically, I'm reducing it to 1 over 1. And then 4 times 1 is 4, over 5 times 1 is 5. So the only time it really matters that they turn into 1s is if I cancel something and then it just disappears. I might have a problem in this situation. N cubed is n times n times n. So when I cancel this and go doink doink, my answer isn't nothing over n squared. What is my answer? 1 over n squared. Because when I canceled those really replaced with 1s. All right. This one I put up here because it's a very common mistake. People think they can cancel the n. You cannot. Why can't you cancel it there, but you could on all the other problems I was showing you? Not because it's the letter n. No. That's not the problem. It's a different kind of problem. How is it different? It's adding. As opposed to these other ones were all multiplications. See, n times n times n, 5 times 2, 4 times 2. Those are all times problems. When there's an add in there, it's not a times problem, and so you can't just cancel those. That doesn't work. It's not a true statement anymore. All right, so that one I can't reduce. It's done. So I'm just trying to show you don't just always cancel because there's one on the top and one on the bottom. You got to make sure that it's actually a multiply problem. Then you can cancel it. If this had been n times 1 over n, then I could cancel it, and the answer would be, technically I'm replacing these with 1s. 1. Times problems, you can cancel. Add problems like this, you can't. What if it's a mix like this? It's got a times and a subtract. So as long as it's a times problem, there's a potential for canceling. That can cancel that. Those can be canceled because it's a multiplication in here. 8 times that z minus 2 and 9 times the z minus 2. So that makes it a times problem, which means this is all equal to 1, which means it can be canceled off. And make 8/9. This one requires a little bit of factoring. Stretch your brain a little bit. Do you remember how to factor the top part here? X squared plus 2x plus 1. It splits up into two little multiplying factors, and it's x, and who can finish it? You need a little number here and here, so that when I multiply them together, I'll get x squared plus 2x plus 1. Yes, sir. You're correct. And then my first, outside, inside, and last would multiply out to this. All right, so now I factored it. Now I can go cancel, cancel, because that's a times problem, that's a times problem. And my final answer would be x plus 1 over 9. Now I knew there'd be some weakness on factoring. I just knew, because that's, that's normal for kids coming into this class, even though we love it for you guys to be awesome at factoring before you come in. But we should take a couple seconds on factoring here because it's so crucial to higher level math. So let's talk about that x squared plus 5x plus 6, that kind of problem. All right. You're wanting to split it up into factors and something plus something like x plus 2 and x plus 5 or whatever it is. Now, to get a little better idea on how to do that, I want to start with foiling. Foiling means first, outside, inside, last. Does that ring a bell? Those are things that you're supposed to know how to do when coming in here. And if I do firsts, it's this and this. And what do I get? X squared. If I do outside, that's this one and this one. When I multiply them, remember this is a big multiply problem, negative 3x. When I do insides, that's the 1 and the x. What's that make? 1x, but I'll just say x. And the lasts are this and, I forgot the negative, and that. Negative 3. Final answer, x squared minus 2x, because those guys can go together because they're like terms, minus 3. Does that ring a bell? You remember how to foil? All right, so factoring is unfoiling. It's like taking this and saying, what would the question have been? And I can look up here and see it's x plus 1 and x minus 3. But if I didn't know that already, I could do, okay, it's got to be an x and an x because the firsts would make that. Outside and inside are the tricky ones. Lasts have to make this. So the point is that this number and this number have to multiply to this. And do you remember the rest of this little story? Those two numbers have to multiply to that and add to that. So you can ask yourself, what multiplies to negative 3 and adds to negative 2? All right, what multiplies to negative 3? Well, it's probably 3 times 1, but one of them's got to be negative. So 3 and 1. One of them's got to be negative. Well, if I make this one negative and this one positive, my results would end up with, when I add them, would end up with negative 2, so that's the way I should do it. Okay, so that's just a quick reminder on factoring. It's supposed to be something that you're good at. Now, if I take fractions, and I talked just about add, subtract, multiply, and divide, you seriously did this in 3rd grade. But we need to make sure that you're good at it so that when we get into the tricky stuff, even by the end of the hour today, we're going to be assigning you stuff that has some big, ugly fractions inside other fractions that you can handle it. So if I add them, I got to have a common what? Denominator. What would be a good denominator for those 14? Just multiply them together, and I get 14ths and 14ths. How do I get 1/2 to turn into 14ths? Times it by 7 on top and bottom. You can always multiply by 1. And that's what I'm doing. Times them by 7 on top and bottom. So I get 7/14ths. How do I get 5/7 to turn into 14ths? I multiply it by something. 2 and 2. That means I really multiplied it by 1 by using 2 over 2. And I get 10 over 14, and I put them together, make 17/14ths. All right. Now some people ask me, do you want us to fix that and make it into 1 3/14ths? No. We actually like improper fractions that are bigger on top. We like those better than mixed numbers because you will never see 1 3/14ths A. And we're doing algebra here, right? And so that happens a lot where we have a variable. You'll never see a mixed number like that. So we like impropers better. So don't have to change this. But what if it had been 18 over 14? Do you think I'd want you to reduce it? Yes, I would. You'd have to reduce it or you couldn't get the full credit. And that can sometimes hurt on tests if you don't reduce something. All right, next thing. Subtracting fractions. Same thing as multiplying them, or sorry, same thing as adding them. Have to have a common denominator. Thankfully, this already does. So I just say that that's 2/4, but I can't leave it that way because I got to reduce it. And the answer is 1/2. Multiplying them. I recommend you multiply them side by side like this. Don't write them like this, where they're like there isn't a top and a bottom. You want to write it so there's a top and a bottom. And on the top, I'd have 8. On the bottom, I have 15. 8/15ths, done. Multiplying them is extremely easy. Just multiply across and multiply across the bottom too. Dividing them, I would never divide. Isn't that kind of weird? How could I never divide? I multiply by the reciprocal. I change this to multiply, and I flip this over and say 20 over 6. Now it's a multiply problem, so never divide. Change it to a multiply. Okay? And then I got 3 times 20 and 8 times... Well, those are going to be pretty big numbers. Could I do some canceling? Yes, I could. The way I like to do that is to rewrite this as 3 over 8 can be broken into 4 times 5 times 20 can be, I just screwed up. Why did nobody stop me there? 8 isn't 4 times 5. 8 is 4 times 2. I will screw up. You don't feel bad about saying, no, and then stop me. Because if I go too far after being a mistake, then it's very painful to have to fix it. All right, so this is 4 times 2, not 4 times 5. And the 4's can cancel now, and the 3's can cancel now. My final answer is 1 times 5 makes 5 over 2 times 2 makes 4, 5/4. Should I make that to 1 1/4? No, leave it as 5/4. All right, so there's a quick power review of add, subtract, multiplying, and dividing, because we're going to get into much more tricky things. Like, what if they're not fractions? Well, then make them into fractions, because fractions work really well with other fractions. You got to make them the same before you put them together. That's a general rule in math. Would you agree if I had somebody said, I'm 3 feet tall, and somebody else said, I'm 73 inches tall? I can't add 3 feet plus 73 inches until I make them the same first. Know what I mean? Got to make the 3 feet into 36 inches, and then I can add it to the 73 inches or whatever. So I got to get them to be the same first before I can put them together. Same with this. They're not. One's mixed. One's a fraction. Make them both fractions. Fractions play nice with other fractions. So 2 1/2 plus 5/7 still isn't good enough. 2 times 2 is 4 plus 1 is 5. 5 over 2. I hope you know how to do that, or you are definitely not going to be able to be hanging with the hard stuff that we do. I can now add them, but now I got to get a common denominator and all that stuff. The moral of the story is change them into fractions first. 2/3 times, how do I make 6 a fraction? What's the easiest way? 6 over 1. You could make it into like 18 over 3 or something, but it's way simpler to just make it over 1. And now I can multiply across the top and across the bottom, and the answer is 12/3. Could I leave it that way? Nope. 4. All right. Subtracting, same idea as the adding one. Dividing, I would never divide. Make this a fraction, though. Change it to a times, flip that over. And now I can do some canceling. The answer is going to be 20 over 1, which is 20. Okay. Let's talk a little bit more about fractions. You might think you're not going to see mixed numbers in the real world. False. The real world actually almost never see whole numbers. You know what this board here that I hold in my hand is called? A 2x4. Yeah. It's named because it's 2 inches by 4 inches. But it's not. A 2x4 is not a 2x4. It's actually, just rough estimate, what's that about? 1.5 inches by not 4 inches, but about 3.5. So a 2x4 is actually 1.5 inches by 3.5. Well, it depends on the 2x4s. There's actually 2x4s that are a little bit bigger than that even. But they're never 2x4. They used to be in the old days. And talking to my dad about it, and we kind of were thinking that it was just a way for the lumber companies to kind of like make a little bit more money because they could make the boards a little bit smaller and nobody'd care. But it actually, I looked up the history of it. In the old days, and I can vouch for this because my dad's dock is made of really old wood. In the old days, the 2x4s were actually 2 inches by 4 inches. And the difference, though, was that they never planed them down to be smooth on the sides. They were really rough. And if a carpenter wanted to do that, they'd have to do it themselves. They'd have to like take a plane and like smooth it out. But the 2x4s came rough. Nowadays, everybody wants their 2x4s to be all soft, so I can like rub it on my face and it doesn't cause any splinters or anything. Okay? And the edges are rounded just a little bit. It's all real nice, but it takes off a little bit of wood. So the lumber company said, fine, but we'll just make 2x4s and we'll just smooth them out on the sides. So that takes off some wood, exactly 1/4 inch on each side, and you end up with 1.5 inches and 3.5. But it's a lot more clumsy to say, would you grab me one of those 1.5 inches by 3.5s? No, so you just say 2x4s, even though it really isn't. All right. Other things on a tape measure. 2 seconds on a tape measure, things you probably never knew. Why are some of the numbers red? At 16 is a red number. At 32, there's a red number. Every 16 inches is a red number. It's because when you're building a wall, there's 2x4s that go up and down in the wall, like this. Those are called studs. And every 16 inches, there's supposed to be a stud. So when they're marking this out with a ruler, they can put a little mark and say, stud goes here and here and here and here, and they can make their studs in the wall. Why this is even cooler does the end of the ruler move? Wouldn't it seem like it would like screw up the length? It doesn't move much, but it moves. Now it's a little bit longer ruler, now it's a little bit shorter. A little bit longer, a little bit shorter. See what I'm saying? It moves up and down. That little end clippy thing on the end of the ruler moves exactly a certain distance. Because if you take the end of the ruler and you grab it onto something like the top of this cabinet, and I pull on it, it will extend out just a little tiny bit. And then when I measure, it'll be exactly accurate compared to if I push it in to like I'm running the ruler across the floor and I push it up against the wall, it pops in a little bit. Why would it need to pop in a little bit as opposed to when I hook it on something pulling out a little bit? That little end piece moves. Why? Because it has to account for the thickness of the little end piece. Because if I push it up against the wall and it didn't move, then the thickness of this little metal piece on the end would throw off the length on the ruler. Probably never noticed that before, did you? All right, so this little end on the ruler is it moves exactly the same distance as the thickness of it. And it keeps the measurement perfectly accurate. Okay, now let's talk about some more things you got to know about fractions. It's multiplying by 1 creatively. Would you agree that I can take anything like this and multiply it by 1? And I won't hurt it. It'll stay the same size as it was. Because like 10/15 is the same as 2/3. Do you get how I can multiply by 1? If I multiply by 1 by using 5/5, it sometimes will be helpful. Why? Well, if I had 2/3 over 5/4, that's a compound fraction, a fraction inside a fraction. To solve that kind, what we want you to learn how to do is to multiply by something on the top and something on the bottom that's equal to 1. In other words, these got to be the same, but that will really make the problem a lot easier. All right. If I multiply by 3 here, do you get how that would make the top not be a fraction anymore? Because the 3's would cancel, and I'd end up with a 2. And now my top of my big fraction isn't a fraction anymore, it's just a number. Do you get how if I multiply the bottom by 4, it would fix the bottom fraction and it wouldn't be a fraction anymore, it would be a whole number, 5, and I could have my answer of 2/5. But what's wrong with what I just did? I multiplied by 3 on the top and 4 on the bottom. I'm not allowed to do that. So who's smart enough to figure out what could I multiply by on the top and the bottom that would fix both of them? I can't multiply by 3. I can't multiply by 4. 3/3, good guess, but no. Seconds ago, we were talking about a common denominator for a reason. 12. Because if I multiply by 12, I'm putting 12 over 1, because I told you before, fractions play nice with other fractions. Then, this turns into, 3 goes in here once, 3 goes in here 4 times. 2 times 4 is 8 over 1, which is 8. This one, 4 goes in here once, 4 goes in here 3 times. 5 times 3 is 15. My answer is 8/15. Do you get what I just did there? Multiply by the common denominator on the top and bottom, and it makes your compound fraction into the answer, like that. All right, so let's try one. On your paper, write this down: 3/5 over 2/3. What are you going to multiply by on the top and the bottom? 15 over 1. You get that? 9/10. All right. Same thing will even work on a little bit more complicated ones. Let's see if you can handle this. Last time we used the common denominator, we just multiplied the denominators. So what do we multiply by on the top and the bottom? I'm going to make it just a fraction like this. So what goes here and here? Come on, you can do this. Last time was numbers. Nope. Thank you for trying. XY. Know why? Because the denominators last time we used were these two multiplied. Well, same thing. Now, why is that going to be helpful? Because look at what cancels. Cancel, cancel. Answer on top, 3x. Cancel, cancel. Answer on the bottom, 4y. Done. Okay? So that's the one new thing that you have learned for today. It's how to clear fractions. You multiply by the common denominator on the top and the bottom, and really that means you're multiplying by 1, and that's why it's legal. All right. A couple other little things you got to know. When you have a square root, you know what the square root of 4 over square root of 9 is? Well, it's the same as this. And I bet you know what the square root of 4 is. I bet you know what the square root of 9 is. That's how you do those kind. This is the kind we just did a second ago. And this kind, you just factor. And if you know how to factor well enough, it'll be like this kind of a thing. Oh, one on the top, one on the bottom. They can cancel. Okay. Your homework is just like that. The answers for it, I hope, will be posted on Schoology tonight. And if they aren't, it's easy enough that you should be able to handle this no problem. Do I expect you to be perfect? No. Do I expect you to be done? Yes. This is due tomorrow. It will go in the gradebook. Yes, sir. I am certain that there is another way I could have done it. Did you get the same answer as me? It's hard for me to tell which one you're pointing at because you're a long ways away. The middle one. Okay, would you multiply it by... Yes, you could take, in this case, it's actually easier to do what you just said and multiply by 4/7 and take 2/3 times 4/7. That is okay. And if you also multiply the top and the bottom by 12, it'll work great. All right, you're going to be out of here very soon. If you need help knowing where your next class is or whatever, let me know. But let's get you out of here even a smidgen early. Have a good day.